All right, let's take a look at a few more examples on antiderivatives for you to add to your notes. This is kind of like when we first learned derivatives. Once you get the rules down, you'll be fine, but in the beginning, it's really going to take some practice. So let's go through a couple more examples here. First of all, let me give you a few more rules. So these are the basic integration rules that go with the trig functions. So the antiderivative cosine x dx would be sine x plus c. And that should make sense because what is the derivative of sine x? That's cosine x. So there you go. The antiderivative of sine x would be negative cosine x plus c. And that should make sense because the derivative of cosine by itself is negative sine x. So the negative in front accounts for that negative in the derivative. So the antiderivative of sine x is negative cosine x. That's the hardest thing to keep straight is which one takes the negative. So if you're ever unsure, just take the derivative of what you have and make sure it gets you back what you started with. The antiderivative of secant squared x is tangent x plus c, and that should make sense because what's the derivative of tangent x? That's secant squared x. The antiderivative of secant x tan x is secant x plus c. Again, what's the derivative of secant x? That's secant x tan x. The antiderivative of cosecant squared x is negative cotangent, kind of like up here because the derivative of cotangent is negative cosecant squared, so the negative there is there to account for that. And then what's the antiderivative of cosecant cotangent? That would be negative cosecant x. And of course all of these take the plus c. Let's try one. What's the antiderivative of 2 sine x dx? So 2 is a constant multiple, so we can save it till the end or think about putting it in the front of the integrand or the integral sign. But what's the antiderivative of sine x? That would be negative cosine x. So our antiderivative is negative 2 cosine x plus c. How about this one, the antiderivative of sine x over cosine squared x? This looks kind of complicated, so let's see if we can use some trig identities to maybe simplify this. You agree that this could be written as 1 over cosine x times sine over cosine x, right? So it's the product of 1 over cosine x times sine over cosine x. And then 1 over cosine x, remember, that's secant x. And sine over cosine x, remember, is tangent x from trigonometry. So this is the equivalent of saying, what's the integral of secant x tan x? And that comes straight from our list. That's just secant x plus c. How about the integral of the cube root of x times x minus 4 in parentheses? So again, we need to get this so that we can apply a power rule because we're dealing with functions that can be written as x raised to some number. So what I would do is distribute the cube root of x first. Make sure you see where this is coming from. I wrote this in my nice handwriting here. So we've got the cube root of x is x to the 1/3, right? So if we distribute the x to the 1/3, we get times the x to the first. That's where the x to the 4/3 came from, because remember you would add exponents, and then x to the 1/3 times 4, of course, is 4x cubed. And then you're just looking at a power rule. So pause the video and find the antiderivative of each of those terms. So what would we have? We would have x to the 7/3 over 7/3, right? Think about this. 4/3 plus 1, 1 would be 3/3, so that gives you 7/3 over the same thing, 7/3. And then remember we have to flip the 7/3, so that gives me 3 over 7 times x to the 7/3. And then the same thing with the x to the 1/3. Add 1 to that, you get 4/3 over 4/3. Flip it so the 3 goes on top, and then those 4's cancel. So that leaves me with 3x to the 4/3 plus c. What if you were asked to solve a differential equation for what's called a particular solution? So a general solution is where we leave the plus c in the answer. But what if we had a question like this? So we have a differential equation because it's got a derivative in it. dy dx equals 3x squared minus 1. If we were to solve this, what we would want to do is integrate both sides. Now, I did an extra step here that I didn't do in the previous PowerPoint, but it's a really, really minor thing. I multiplied this dx to the other side so that that's called separating the variables. So I have the y on the one side and dx on the other side. And then you're integrating both sides is really what you're doing. So the antiderivative of dy, that's like a 1 in front of it, but you're integrating with respect to y. So that's where the y on the left side technically comes from. We didn't go through those steps in the example I showed you in the last PowerPoint. I'm not so concerned about all the separating the variables and all that, but do you see, make sure you see what we're doing. To solve this, I'm integrating 3x squared minus 1. So the integral of 3x squared minus 1 would be x cubed minus x plus c. So this is called the general solution to the differential equation because it's got the plus c in there. But what if they also told you that the solution goes through the point 2, 4? So big F of 2, 4. What they're doing is they're giving you information that we can use to find what the particular C value is. That's called the particular solution. That's where this term comes from. This is called an initial condition. Like I said, I know there's a lot of vocabulary in this section. Just roll with it. You'll get the hang of it. We'll use a lot of this vocabulary in class. And as we go through examples together in class, you'll see that this isn't as bad as it sounds with all the terms. But for now, just know that this is called the initial condition. And so this means that the curve that we're interested in for the antiderivative, we want it to contain the point 2, 4. So what we're going to do is we're going to substitute in the 2 in place of the x's and the 4 in place of the y. And what that does, it allows us to solve for c. So if I crunch the numbers here, move the term to the other side, we get a c value of negative 2. So what that means is our particular solution is y equals x cubed minus x minus 2. So we have a general solution, leaves the plus c in there, but if they give you this initial condition, you're going to plug those numbers in to find your particular c value that they want. Let's try one like that. Find the particular solution that satisfies the initial condition f of 1 equals 0 in the differential equation. Now notice I didn't give it to you as dy dx. Instead I gave it to you as f prime of x, but it's the same thing. This is a differential equation because it has a derivative in it. So we're told that f prime of x is equal to 1 over x squared. So to solve this, we're going to find the antiderivative of 1 over x squared. I'm going to write that as x to the negative second. I'm going to use the power rule. So that would be x to the negative first over negative 1, which gives me negative x to the negative first, or negative 1 over x plus c. Now we need to find the c value because they gave me an initial condition. So I'm going to plug in 0 for the y, 1 for the x, and when I solve for c, I get a c value of 1. So my particular solution to this differential equation is f of x equals negative 1 over x plus 1. Okay, let's look at one more example here. It says, assume a ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. Assume the acceleration due to gravity is negative 32 feet per second squared. So it says, find the position function giving the height s in terms of time t. So think back to earlier in the course. Remember there was a relationship between position, velocity, and acceleration. Remember PVA. So if position was given to you, velocity was the derivative of the position, and acceleration, remember, was the derivative of velocity. So they're asking us to find the position function, and we're given some information about acceleration and velocity. So we're going to work backwards here. Let's first of all write down what they told us. They told us that at time t equals 0, the initial height was 80. So the position, I'm using s because that's what they asked me to use for position for the height, s of 0 equals 80. That's like an initial condition. They also told me the initial velocity, so that means at time t equals 0, the velocity was 64 feet per second. So if s is position, s prime at 0 is 64. And they told us to use negative 32 feet per second squared for velocity. So what we know right now is that negative 32 feet per second squared for acceleration. I misspoke there. So negative 32 feet per second squared is our acceleration. So that means that s double prime, if s is the position, the second derivative is the acceleration, is equal to negative 32. So how am I going to work backwards from there to find the velocity function? We'll go through it one by one. Let's work backwards to find velocity. That means we're going to find the antiderivative, or the integral of the acceleration, right? If I know the second derivative, I want to go backwards, that's an antiderivative. So the antiderivative of negative 32 with respect to time, so dt, would be negative 32t, because that's a constant, right, plus c. Now, how do we find c? Well, they told me the initial velocity was 64 feet per second. So that means that the velocity, or s prime, at 0 is 64. So if I plug in 64 over here and 0 for time, I get a c value of 64. So my velocity function, s prime, is equal to negative 32t plus 64. Now, if I know velocity and I want to work backwards to find position, what am I going to do? I'm going to find the antiderivative of the velocity function. So pause the video, and I want you to find the antiderivative of this expression, negative 32t plus 64 with respect to time. So that'll be negative 32t squared over 2, because it's a power rule, plus 64t, 64 is a constant, plus c. I'm going to simplify the 32 over 2 and give me negative 16t squared plus 64t plus c. Now, how am I going to get this new c value? Well, remember, we also had this information about the initial height. We were told that at 0, the initial height was 80. So if I plug in 0 for my time and 80 for my height, I can solve for c and get 80. So my position function for this object is negative 16t squared plus 64t plus 80 is equal to s of t. Now, there was a part B to this question, and part B said, when does the ball hit the ground? So think about when the ball hits the ground. That would be when the position equals what? The position would equal 0. So I'm going to set this equal to 0, and I can factor out a negative 16. I'm going to skip the details for now, but I'll factor out a negative 16 and then factor the remaining trinomial, and I get values of negative 1 and 5. Which one makes sense in this context? Of course, that would be at 5 seconds, since we're not going to have a negative time value.